Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of our unit Mechanical Properties of Fluids. So let's begin with today's class. In today's class, we are going to discuss about the concepts of the fluid pressure. But before we go to the fluid pressure, we need to understand these two words. A first word would be a fluid and another would be a pressure. Let's understand them one by one and then we will switch to the fluid pressure. So first, let's understand what fluid is. We can say fluid is a substance that can flow. So the everything that can flow can be considered as a fluid. So the term fluid includes both liquids as well as gases, and fluid plays a very vital role in our day-to-day life, that we understand that everything that is fluid, even water is a fluid, blood is a fluid, and every gases can be considered as a fluid. Now let's discuss what pressure is. We can say pressure, it's a thrust exerted by liquid at rest per unit area, which is normal to the surface in contact with the liquid is called as the pressure of a liquid. This pressure P, that could be said as the force by area, and this is the total force, that is the total force exerted by liquid on any surface in contact with it is called as the thrust or pressure of the liquid. This pressure could be given, it's in force by area. SI unit of pressure, it's a Newton per meter square. CGS unit of pressure, it's a dyne per centimeter square, and we understand that 1 Newton per meter square is equals to 1 Pascal, because and we know this, it's a pressure P is equals to force by area. So if I want a dimensional formula of the pressure, it's a force which is equals to kg into meter per second square. Area, it's a 1 by meter square. So this is meter, this is 1 by meter square, this is kg upon meter into second square. It's an m1 l minus 1 t minus 2. The pressure at a point in a fluid is independent of the direction, and it is the scalar quantity. Pressure is a scalar quantity. Now, which are the different units of the pressure other than Newton per meter square or Pascal or dyne per centimeter square? The one of the unit is 1 atm, that we call as an atmospheric pressure, which is equals to 1.01 into 10 to the power 5 Pascal. Yes, this is one of the unit, it's an atm. Then other than this, yes, it's a 1 torr. Next, it's a certain centimeter or millimeter of mercury, Hg. Next, one more, yes, it's a bar. So this all are the units of the pressure that we use conventionally, and Newton per meter square or Pascal is the SI unit. Great. Now let's look at the density of a fluid, which is indispensable in describing fluids. The density that we denote as a rho. Let's have a fluid is having a mass m and which occupies a volume of v. So when I find the density, it is the ratio of mass to the volume. So this is density, which is equals to mass divided by volume. SI unit of density, it's a kg per meter cube, and CGS unit of density, it's a gram per centimeter cube. Dimensional formula of density, it's in kg per meter cube, that means m1 divided by l3 or m1 l minus 3. Again, it's a positive scalar quantity, that means it can have only the positive numbers and could not have any negative numbers. I hope this is clear. Is it clear? Great. Now let's look at the questions based on the pressure. Let's suppose this is a table, and when this is a table, I have kept one of the box over here, and this box is having mass m. So the question would be, find out pressure acting on table due to box having mass m, and this is its dimension, it's an L by B. So what I understand is that if I want to write the pressure, that could be given as force by area. This force, only one force is acting on it, which is equals to mg. So this is equals to mg divided by cross sectional area, it's an L into B, Pascal. This would be our answer. I hope this is clear. Is it? Is it clear? Let's work for the next question. Do it quickly. Let's suppose we have been given another table, and on which let's suppose a certain this kind of cylinders, but having different cross sectional area on both the sides. This is in contact, having radius r1. This is not in contact, or another surface, it's an r2. This is having mass m. So they can ask me that find out pressure acting on table. So again, I'm having the one relation only, it's a pressure is equals to force by area. The force acting, it's an mg. Now divide by area. Which area I should take? Should I take pi r1 square or should I take pi r2 square? So when this kind of situation occurs, always remember that it is the area in contact. So this area is in contact and this is not in contact. So I should take, it's a pi into r1 square, Pascal. Have you got this? Did you? Are you sure? So do you understand this completely? Have you? Great. Now let's work on the pressure due to fluid column. Let's look at this, that we have this container and the cross sectional area of the container is the A, and we have filled a fluid in this container up to height h, and this fluid is having density of rho. So what the pressure is, when I say pressure, it's a weight of the fluid divided by cross sectional area. So let's assume that weight of the fluid, it's a m into g, divided by cross sectional area, it's an A. If I want, I can replace mass m with the relation which is equals to density is equals to mass by volume, and from this it's mass is equals to density into volume. Volume could be written as cross sectional area A multiplied by height h. So this mass m could be replaced, it's a rho into A into h into g, divide by cross sectional area A. So this has gone, and this is equals to h into rho into g. I hope this is clear. So this is the pressure, this is the pressure, and which depends on the height of the liquid column as well as the density of the fluid. It's a pressure due to liquid column, it's directly proportional to the depth of the point below the free surface of the liquid, and it also depends on the density of the liquid. I hope this is clear. Is it clear? Is it? So this is P is equals to H into rho into G. I hope this is clear. Yes? Great. Please do remember this. We will be back on this, but before we go through the numericals of this, let's discuss even this point. It's an effect of gravity on the fluid pressure. Now let's suppose, what we have supposed is that we have considered 2 points. One is the P, another is the Q, and the separation between these 2 points is the H. So H is the distance between block P and Q, and A is the area of cross sectional. Again, what we have taken is we have taken an imaginary cylinder, and for that imaginary cylinder, point P A is on the upper surface and point Q, it is on the lower surface. We can understood that weight of the imaginary cylinder that would be equals to m into g. If it is equals to m into g, if let's say it is equals to m into g, then m could be replaced by density into volume, and volume could be replaced by a into h, as we have done in the previous slide. So the weight of the imaginary cylinder, it's an a into h into rho into g. Let's suppose that P1 is the pressure at point P and P2 is the pressure at point Q. So if it is the pressure at point P and pressure at point Q, that means force at point P could be written as F is equals to P1 into A, because we understand that pressure equals to force by area. So from this, it's a force which is equals to pressure into area. It's a pressure into area. Yes. So force at point P, that could be written as F is equals to P1 into A. That means a total downward force in this direction, it's a P1 into A plus mg, and vertically upward force is F2 is equals to P2 into A. I hope this is clear. Yes. And as this cylinder is at equilibrium, that means net force acting on it is zero. Neither it is moving downward direction, neither it is nor it is moving in the upward direction. So as this is the situation, we understand that total downward force should be is equals to total upward force. If total downward force and total upward force is equal, that means F1 is equals to F2. When I say F1 is equals to F2, it's P1 into A plus mg. That should be is equals to P2 into A. And from this it's a P2 minus P1 into A. That should be equals to mg. So this is the P1, which is the pressure at point P. This is the P2, which is pressure at point Q. I hope this is clear. Yes. So basically this is the P2 minus P1, which is equals to A into H into rho into G, and this is gone. So from this I could have this relation. Look at this. This is very useful relation. It's a P2 is equals to P1 plus H rho G. I hope this is clear. Is it clear? It's a P2 is equals to P1 plus H rho G, and let's look at the special cases of this. That this was the situation. This was the container, and this container has been filled with this fluid. Let's suppose we have a certain point over here, and this is height h1. Let's call this h1, and let's call this point as an A, and we have different point at here. This is point P, and let's say this is height h2, and we have one more point over here. This is height h3. So let's say on this top of the surface, as we have understand in the previous classes, that this pressure is the atmospheric pressure. So if I want to write pressure at A, that could be simply given as that pressure at A would be equals to PA plus height of the liquid column, it's a H1, multiplied by density of the liquid, which is G, multiplied by G. That's it. You did it. Great job. Same way, if I want to write pressure at B, that would be equals to pressure of atmospheric pressure plus height of the liquid column, which is equals to H2 multiplied by density of the liquid multiplied by G. Same way for this H3 height, it's a pressure at, let's see, call this as a C. This is equals to PA plus H3 into density of the liquid into G. So I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Do you? Do you have any doubts? So can you do this? Can you? Are you sure? Great. Let's work for one more question. Let's suppose this is the container, and as this container is being filled with the fluids. If this container is being filled with the fluid, let's call this is point 1, this is point 2, and this is point 3. Named it, it's an A, B, and C. This is 10 meter. This is, let's call it 5 meter, and this is 2 meter. Find out pressure difference between point A and C and A and B. Density of the fluid, it's 1000 kg per meter cube. Which liquid is it having density 1000 kg per meter cube? Do you know this, that density of which fluid is 1000 kg per meter cube? Yes, it's a water. So density of water, it's 1000 kg per meter cube. If I write this in SI unit, and density of water, it's 1 gram per centimeter cube. Please do remember this if I write this in CGS system. So now let's back to the question. It's a pressure at A. What I should write? It's a PA plus 10 multiplied by density into G. It's PB, which is equals to PA plus it's a height, which is equals to 5 multiplied by density multiplied by G. It's a PC, which is equals to PA plus it's a 2 multiplied by density of fluid into G. Now what I want the difference of them. It's a point A and C. So let's find it out. It's a PA minus PC. As you can observe that this PA got cancelled. This rho g would be there. This is 10 rho g, this is 2 rho g. So it would be a 10 rho g minus of 2 rho g. This is equals to 8 into density of liquid into G. This is 8 into 10 to the power 3 into 10, which is equals to 8 into 10 to the power 4 Pascal. I hope this is clear. So this is pressure difference between points A and C. Next, it's a pressure difference point A and B. This is equals to PA minus of PB. That is equals to this PA got cancelled. And when this 2 got cancelled, it's a 10 rho g, this is 5 rho g. So this will be, it's a 10 rho g minus of 5 rho g. This is equals to 10 minus 5, which is 5 into rho into G Pascal. I hope this is clear. Is it? Did you get it? Are you sure? Now, do you have any doubts up till now? Is there anything? Now let's discuss in more detail about the atmospheric pressure. That what atmospheric pressure is. Let's have a look. It is the pressure of the atmosphere. It is the pressure of the atmosphere at any point that is equal to the weight of a column of air of the unit cross-sectional area extending from that point to the top of the atmosphere. So basically it is this situation, that let's understand that if you want to find out atmospheric pressure on this rectangle, what you need to do is you need to find out a weight of air from this box to top of the atmosphere divide by its a cross sectional area. Let's call this L into B. This is what we call as the atmospheric pressure. At sea level it is 1.013 into 10 to the power 5 Pascal, and that is what we call as a 1 atm. It's a 1 atm which is equals to 1.013 into 10 to the power 5 Pascal. Now The second question what came into my mind is how should I calculate the atmospheric pressure? So we have a device for it, and that is what we call as a barometer. So barometer is a device which is used to measure the atmospheric pressure, and it consists of a long glass tube which is closed at one end, and it is filled with the mercury, and it is placed in a mercury through in the inverted position as shown in the figure. Look at this diagram. This was the situation, that this is the container, and in this container this has been filled with the mercury, and a glass tube like this has been inverted in this. Yes. So the space above mercury column, so it will look like this, that certain times, yes, so it has been filled up to this. The space above mercury column in the tube contains a mercury vapor whose pressure P, this is the mercury vapor here would be there, that can be neglected, and the pressure at A and B are equal. Look at this, this is A, this is B, which are at the same level. This is how barometer works. So at any point, if I want to find out the pressure, I could have, it's a PA which is equals to rho into G into H, where rho, it is the density of the mercury, and H is the height of the mercury column. It was found that the height of the mercury column, it is found that the height of the mercury column is 76 centimeter at the mean sea level, which is equals to 1 atmosphere. So I could write like this, it's a 180 m, which is equals to 1.01 into 10 to the power 5 Pascal, as well as this could be written as 76 centimeter of mercury, or it's a 760 millimeter of mercury. It's a 76 centimeter of Hg, or 760 mm of Hg. I hope this is clear. Was it clear? Was it? Are you sure? Did you get this? Have you? Great. So this is what barometer is. Now let's discuss the different pressure. It's a what we call as a gauge pressure. Basically, it's a pressure difference between actual pressure P and the atmospheric pressure PA. That is what we call as a gauge pressure, or sometimes someone pronounce it as a gauge pressure. Yes. So it's a gauge pressure which is equals to P minus PA. Now, the again the question is how to find out the gauge pressure. Let's have a look. Let's suppose understood that on this surface where air would be there, this is the atmospheric pressure, and let's suppose I have denoted it as a P naught. And on the container we have a certain fluid which has been filled up to height h, and the density of this fluids, let's call it's a rho. So at the depth, at this layer, the pressure due to liquid is that one pressure it's a P naught, and another pressure it's a P. This is pressure due to fluid, this is pressure due to atmosphere. So this total pressure, that's P total, could be written as P naught plus H rho G. So it's an excess of the pressure which we call as a P minus P naught at depth H is called as the gauge pressure at that point. Or I should write this, it's a total pressure is equals to P naught plus gauge pressure. Or I should always understand that total pressure minus P naught, that would be the gauge pressure. I hope this is clear. Now it is clear that what gauge pressure is, but who will be going to measure this gauge pressure? We have a device which we call as a manometer, and this is how manometer look alike. So a manometer is device which is used to measure the pressure differences, and it consists of a U tube containing a suitable liquid, as you can see this from here to here, for measuring for measuring the small pressure differences, a less dense liquid is generally used, and for measuring the large pressure differences, high dense liquid like mercury is used. So this is the fluid density. Here we are going to fill up the fluids. Here the another fluid would be there, and as you can see that this is balancing over here, and they can find out the pressure difference. They can find out the pressure difference. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Any confusion? Is there anything? No? Yes. So in this situation, it's a pressure at A, as you can see this, that let's call this as an A, and this pressure at A could be written as, here atmospheric pressure would be there. It's atmospheric pressure plus height of the liquid column multiplied by density into G. So this PA minus PA, because PA is the total pressure over here. So PA minus PA, which is we call as a pressure difference, which is going to be measured by the manometer. It's an H2 into rho into G. I hope this is clear. So now we understood that basically we have a we have two devices to measure the pressure. To measure the pressure, we have two devices. Basically we have two different pressures too. One is the atmospheric pressure. It is the atmospheric pressure, and another it's a gauge pressure. And to measure this two different pressures, we have different device, or we can say apparatus for it. To measure the atmospheric pressure, we have the barometer, and to measure the gauge pressure, we have the manometer. I hope this is clear. Is it clear? Are you sure? So now, do you understand everything up to this, or do you have any doubts? Do you have any doubts up till now? Have you? Have you? No? Great. Now let's understand one of the very critical concept through a numerical. Let's suppose this is a container and it has been filled with the fluid. Let's suppose point A is over here, point B is over here. This is height h, this is height h. Yes. So if I want to write that pressure at A, what it would be? It would be an atmospheric pressure plus h multiplied by density of fluid multiplied by G. If it is the pressure at B, then it would be a pressure of atmospheric pressure, which we call as a P naught, plus height of the liquid column multiplied by rho into G. And let's suppose a one of more point would be there. This is point C. This height let's we call as a CH1. So again, for pressure at C, which is equals to P naught plus H1 into rho into G. I hope this is clear. Is it clear? Is it? Are you sure? Now, do you have any doubts? Is there anything? Is there anything? No? Great. So from this observation, I can have a came to a conclusion that when fluid is at rest, when fluid is at rest, pressure at same horizontal level, pressure at same horizontal level will be always same. Please keep this in mind. Yes, when fluid is at rest, pressure at same horizontal level will be always same. Even we are going to prove this with the help of one of the law that we call as a Pascal's law. But even if we don't know what Pascal law is and how that has been derived and everything, we can have this kind of observation that first condition is it should be at rest. If it is at rest, then pressure at same horizontal level of course we are talking about the same fluid. For same fluid, yes. So so pressure at same horizontal level will be always same, and in this case we are talking about the same fluid. Yes, even if this is not the condition, this can be verified easily, that we will see in the upcoming session. I hope this is clear. Is it clear? Is it? So let's do a question based on this concept that pressure will be same or different. Let's suppose we have this kind of liquid column, and this is point A, this is point B. So find pressure difference between point A and B. You need to find out the pressure difference between these 2 points, between points A and point B. How will you do this? What is to be done? Yes, as you can see this A and B both are on the same level. So pressure at A would be equals to pressure at B. Why? Because they are on the same horizontal level. And as they are on the same horizontal level, the pressure difference delta P, which we call as a PA minus PB, that would be 0. This is what pressure difference is. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's work for the next question. Let's suppose this is the container and it has been filled with the fluids, and let's suppose one of the point is over here. This is A. One of the point is here, and this is of, let's say, x centimeter, and with horizontal, let's suppose this makes an angle of 30 degree. So they ask the same question, find the pressure difference between point A and B. How will I do this? So when I write this pressure difference at A and pressure difference at B, how will I do this? What do you think for this? What do you think for this? This is x centimeter, so if it is the dimension, this is x cos 30 degree, while this height will be x sine 30 degree. So it is basically the pressure at A minus pressure at B. The PO has been cancelled out. Only the thing that has been left is the H into density of liquid multiplied by G. When I say it's an H, it would be the x sine 30 degree multiplied by density of liquid into G. While I say it's an x sine 30, while I say it is the x sine 30 degree, that means it is the x sine 30, it's a root 2 multiplied by rho multiplied by G. I hope this is clear and you got this. Have you? Have you got this? Are you sure? Now do you have any confusion over this? Any? No? Great. So do you understand up till now? Have you got this? Great. Let's work for the next questions. Suppose the question says that, let's suppose that we have this kind of tube. It is generally what we call as a U-shaped tube, and this tube is filled with two different fluids. Suppose this is one fluid having density rho 1, and this is height h1, let's suppose. And on the other side, it has been filled with this different fluid, and this is having density of rho 2, and this is having a height of h2. So if they ask me that find out h2 of liquid if if system is in equilibrium, even if this is not being given, even if this is not being given, the system by itself is in equilibrium if it is not in motion. First thing, if it is not in motion, then it is going to be by itself only, it is going to be in the equilibrium. So what you can understand is that this is the fluid 1 and this is the fluid 2. The both are going to be balanced over here. This is the boundary where they are balancing, and if this is the location where they are balancing, that means a pressure at this point, let's call this as a pressure at A, and pressure at this point, which we call as a pressure at P, this two pressure must be equal, because they are the pressure which arrange their height like this. Yes, so we can say it's a PA, that should be is equals to PB. And while I say PA is equals to PB at this point atmospheric pressure would be there, which is equals to P naught plus H1 into rho 1 into G. That is equals to PB, which we call as a P naught plus H2 into rho 2 into G. So this P naught and this P naught has been over, and with this P naught and P naught has been over, this GG got cancelled out. So from this it's an H1 rho 1 is equals to H2 rho 2. So basically we have four variables: height 1, rho 1, height 2, rho 2. Any three of them will be given, and fourth will be calculated easy, as in this case H2 has been asked. So this is equals to H2 is equals to H1 rho 1 divided by rho 2. That's it, you did it. Great job. I hope this is clear. Is it clear? So, do you have any doubts up till now? Do you? Do you have any doubts? Are you sure? Are you sure? Great. Now, let's work for the next question. Let's suppose again a U-shaped tube has been given, and in this U-shaped tube, let's suppose a two liquids has been filled. One of the liquid is having density rho 1, this is rho 1, and this other liquid is, let's yes, this is having density of rho 2. Now they have given me the heights, such as this is h1 and this is h2, and this is x. Yes, this all are the dimensions they have given me. This all are the dimensions. So again, let's suppose they will ask me find out density of second liquid. You need to find out the density of the second liquid. How will you do this? How will you do this? What can be done? So what we can consider is, at same horizontal level, at same horizontal level, pressure will remain same. And if I consider the pressure will remain same, that means I could have this relation that this at this point, let's call this at a pressure at A, let's call this as a pressure at B. At this point, pressures will be equal. So from this, it's a pressure at A that would be equals to pressure at B. Now, what is pressure at A? It's a P naught, which we call as an atmospheric pressure, plus height of the liquid column above it. It's an H2 plus X. So this is H2 plus X. It's a height multiplied by density of liquid, which is rho 2 multiplied by G. That is equals to PB. That A is equals to PB. This is equals to P naught plus even this height, it's an X. So this is equals to X into density of this liquid, which is rho 1 into G. This P naught and P naught got cancelled, and what I am having, it's an H2 plus X into rho 2 into G. That is equals to, it's a H sorry, X1 multiplied by rho into G. This is the situation. So from this we can have this G and G got cancelled out. So this is equals to rho 2 is equals to X divided by H2 plus X multiplied by, this is rho 1. Sorry, I hope this is clear. Was it clear? Was it? So this all are the very easy questions, but they have a probability to be asked. uh, every year time from last 2 years, a NEET examination has started asking this questions. Even if you go through the different sets of the JE, you will find this kind of questions. And this has been started asking from where NTA has started. Yes, so it is having a very high probability nowadays to be asked. Please keep this in mind. I hope this is clear. Now, will you be ready with one more question? One more question. Let's have a look. Let's suppose one of the U-shaped tube has been given, and now in this U-shaped tube we have three different liquids. One of them is having density rho 1, one another is having a density of rho 2, something like this, and one more which is having density rho 3. I hope this is clear. Is it? Now they have given me the dimensions that, let's call this as an H3, this as H2, and this as H1. So how shall I write the relation? As I understand that fluid at the same pressure, same horizontal level will be at the same pressure. But how to write this? I can choose this point, that this is pressure at A, this is at pressure at B. If you think that, sir, why to choose that point only? Because even we have a probability to choose this boundary as well, because they are even on the same horizontal level. So yes, you are right that even you can choose that based on that horizontal levels, but the problem is that when you write the density for relation for this, and when you write pressure relation for this, You will be having only the relation with density 1 and density 3, but not on the density 2. So it is not like that, because this balancing condition or this equilibrium condition has been achieved due to rho 1, rho 2, rho 3. With all three makes this system is an equilibrium state. I hope this is clear. So they are on same horizontal level. Yes. Should we use them? I should say no. We need to always choose a point. We need to always choose a point for which we could have relations for everyone. I hope this is clear. So this is going to be chosen, and that is what we call as a PA is equals to PP. Now while writing PA, let's call this as an H4. This height, it's a P naught plus this height is H4, and this complete is H1, this is H3. So this height is H1 minus H3, and this height is directly the this height, it's an, yes, even it is H1 minus H3. So pressure at A, it's a P naught plus H4 plus H1. Give me a moment. It's this row 1. This row 1 is up to here, and so this is equals to H1 minus of this height, it's an H2 into row 1 into G plus for this height this is the H2 minus H3, it's an H2 minus of H3 multiplied by rho 2 into G. This is equals to pressure at B. This pressure at B will be equals to P naught plus it's an H1 minus H3 multiplied by density of 3 into G. That's it. So G could cancel, P naught could get cancelled, and you can easily find whatever you want. I hope this is clear. Is it clear? Is it? So now do you understand what is to be done and what would be the situation? Have you got this? Have you? Do you have any any problem with this? Is there anything? Do you have any doubts? Are you sure? Are you sure? Can you do this? Can you? Great. Now, now let's understood that if this fluid is in motion, if container filled with fluid is having accelerated motion, let's see what will be the situation if container is in motion. What will happen? Let's have a look. Let's suppose this is the situation, that this is the container, and basically it's a trolley which can move. Let's suppose it is moving in this direction with acceleration A. So if this container is moving like this with accelerated motion, the shape of this fluid would be varied something like this. I hope this is clear. Is it clear? Yes. Is it clear? Are you sure? And this is moving, yes. Now let's assume that 2 points, this is, let's say, point A, and this is, let's say, point B. So now this is the situation, this is point A, this is point B. Length between this, it's an L. Yes, the length remains the same. This is the length. And this point A is at height of h1, and point B is at of height of h2. I want the pressure difference between these two. I want the pressure difference between these two. So how will I do this? What can be done? Shall I redraw this? That this was the situation. This was the container, and as it is in motion, or I should say it is in accelerated motion. Yes, it is something like this. And this point is at A, this point is at B, this is length L, this is height h1, this is height h2. Now what should be the value of the PA and PB, and how to do this? So from this I could have the relation which is equals to PA, which could be given as it's a P naught plus H1 into density of liquid into G. I hope this is clear. What would be the PB? It is basically the P naught plus height of the liquid column H2 multiplied by density of liquid multiplied by G. So this is PA, this is PB. I hope this is clear. Is it clear? Great. One more thing. If I write down all the forces, and according to the length, according to the Newton's laws of motion, what I can do is that I can create an imaginary cylinder over here, and this cylinder is having length L and cross-sectional area A. So what I can write is the PA minus of PB, that is equals to rho into area into length, it's a volume, multiplied by acceleration. I hope this is clear. So it's a PA minus PB multiplied by cross sectional area, it's a force multiplied by area, sorry, pressure multiplied by area, which will give me the force, and this is equals to, this is equals to force is equals to M into A. I hope this is clear. So from this cross sectional area has been lost, and this is what we can write, it's a PA minus PB, that is equals to density of fluid multiplied by length between this two multiplied by cross sectional multiplied by acceleration A. It's a rho into L into A. So let's understand that this is first relation. If I take a difference of this, it's a PA minus PB. It's a PA minus PB, for which P naught has been gone, and if P naught has been gone, this is equals to H1 minus H2 multiplied by rho into G. I hope this is clear. One more thing is that you can see this at this kind of triangle as well. This is theta, and the difference of them, a difference of this heights, is h1 minus h2. I hope you understood this. Have you? Have you understand this? Great. So let's call this as a relation 2. This was the relation 1. From this 2, if I equate this, because both are the value of PA minus PB, which is equals to H1 minus H2 into density into G. This is equals to rho into L into A. So this rho could be given, rho could be cancelled out, and this could be written as, which is equals to H1 minus H2 divided by L, or that could be given as A by G. But if you see this, this is the value of tan theta. From this, it's a tan theta, which is equals to H1 minus H2 divided by L. So this could be written as tan theta. This is the relation which is very important. Please keep this in mind. This tan theta is equals to H1 minus H2. It's a difference between two layers. It's a difference between two levels of the fluid. Divide by length between these 2 points. It's an H1 minus H2 by L. That should be is equals to A by G, and that is equals to the tan theta. I hope this is clear. Is it clear? Is it? Even this is valid in this kind of U tube. Let's have a look. That this is U-shaped tube, and it is filled with the fluid, and now let's suppose it is moving or it is having the accelerated motion, and its fluid will be something like this. It is theta, and this is the L. So even I can write like this, it's a tan theta. Let's call this as an H. It's a tan theta, that would be equals to A by G, as well as it's a height difference between two layers divided by length. It's a tan theta which is equals to H by L. I hope this is clear. Is it clear? Now do you have any doubts? Is there anything? Do you? Do you have any doubts in this? Are you sure? So, will you be able to solve this kind of question? Will you be? Let's have a look. Suppose we have a container. This is the container, and it is moving in this direction, and due to its motion, the shape of the fluid is something like this. Now, let's suppose this is point A, this is point B. At this point, this is point C. This is, let's call as an L, or I should say L1. This is what we call as an H2, because this is H1. So let's write down the pressure at A, what it would be. What it would be. So first thing, it's a P naught plus H1 into density of liquid into G. Let's write down the pressure at B, which is equals to P naught plus H2 multiplied by density of liquid into G. Let's write down the pressure at C. Now the pressure at C, it's a P naught only. What I can see, it's a P naught only because it is at the topmost position. Yes. Now let's suppose if I have been asked the pressure at A minus pressure at B, what I could write? That could be written as density of liquid multiplied by length between these two into A. I hope this is clear. Suppose I have been asked PB minus PC. So that could be written as it's an H2 into rho into G. I hope this is clear. If now one of the very important question is if I have been asked the PA minus of PC, it's a pressure at A minus pressure at C. So what I need to do is I need to break this task into two parts. It's a PA minus PP plus PB minus of PC. Now I'm having the value of both. Look at this. So from this I can easily get it done. It's a rho into L1 into A plus H2 into rho into G. This is pressure at A minus pressure at C. I hope this is clear. It's a density into L1 into A plus H2 into rho into G. I hope this is clear. Was it clear? Are you sure? Now do you have any doubts? Do you? Is there anything? Is there anything? No? Great. Ready for next question? Ready? Let's have a look. Suppose this is the container and it has started moving in this direction with acceleration of 20 meter per second square. So they will say that find the difference between heights of fluid when container starts moving with 20 meter per second square acceleration. So how will you do this? As we understand that as it starts moving, it will look like this, and this is the difference. Yes. So let's call this as an L, and let's call this as an H. So it is basically a tan theta, which is equals to A by G, which is equals to H by L. Let's call this L as a 10 centimeter. So as I can equate this to, it's a A by G, which is equals to H by L. If I'm doing this, it's an acceleration which is equals to 20, G is the 10, H I don't know, L is the 10 centimeter. It's a twin twos. So H is equals to 20 centimeter. There is a difference of height of this much, which is equals to 20 centimeter, 20. I hope this is clear. Is it clear? Is it clear? Are you sure? Now, do you have any doubts? Do you have any doubts? No? Are you clear with this? Are you? Do you have any doubts? Is there anything? Is there? No? Great. Now let's look at this question. Suppose we have, suppose we have this kind of fluids, and let's say this is the container, and this container is filled with the fluid. Now let's suppose this is the axis around which it starts rotating with an angular speed of omega. Yes. And now what happens? If this starts rotating with angular speed of omega, this shape has been changed. It is something like this. I hope you understand this. Let's call this point a y. Let's call this point a y. And I need to find out this value of y. So how will I do this? What could be done? What could be done? What I understand is that let's suppose exaggerated this in this manner, that this was the situation, and with about this, let me redraw. About this, it starts rotating, and if I take this point, let's suppose if I took at this point, this is P, then on this point there is a force which we call as the, it's an m into x into omega square. This point, it's an mg. So this is the theta, or I should say this is the net force that is acting. Yes, even if this is theta, even this would be the theta. And now from this I can have this relation, it's a tan theta, which is equals to mx omega square divided by mg. So this has gone, and that could be, that tan theta could be also written as, this is what we can say is, this is the dx, and let's call this as a dy. So from this it would be a dy by dx. This is equals to omega square into x by g. I hope this is clear. So if it has been extended up to height y, if it has been extended up to y, this could be written as that this was the situation, it was a dy by dx. This is equals to omega square into x divided by g. So from this it's a dy, that is equals to omega square by g multiplied by x dx. Let's integrate this on both the sides. If I am going to integrate this from 0 to y, this is going to be integrated from 0 to x. Integration of dy, that will be given as a y. This is equals to omega square by g into integration of x dx, which is equals to x square by 2. This is equals to 0 to x. So from this it's a y, which is equals to omega square x square divided by 2 into g. This is y. I hope this is clear. Was it clear? Was it clear? Are you sure? Do you understand this? Great. So let's just wind up this session over here. This was the all about the fluid pressure when fluid is at rest, and then we have even seen the and derive the relations and observe the situations when carts fluid uh, filled with the fluids are in motion, or I should say they are in accelerated motion. What would be the pressure difference and everything? So please do this kind of questions. This have a very high probability to be asked. Visit and check all the previous year asked questions. You will find that there is a one question that has been asked from the U-shaped tube, and different fluids will be filled, and different questions can be came from this side. So please do this, please do this. This will help us to get it done very easily. So this is high time, and we need to focus on this, that every questions must be attempted by us in a correct manner. So please do as many questions as possible. This will help us and this will save us. Thank you. Have a good day. Take care. Bye bye.